Hi, everyone. My name is Matthew Kowal, and I'll be presenting our paper on quantifying static and dynamic information in deep neural networks. So deep spatiotemporal models have been shown to be really amazing at a variety of tasks, right? Like action recognition or video object segmentation, but it's still not learning in order to solve these tasks. And for example, in action recognition, it's been shown in previous work that action recognition models are actually biased towards appearance information as well as the background scene. And many benchmarks are actually solvable from a single static frame, right? And this gives rise to a underlying problem in the field, which is that there's still no good metrics for quantifying static and dynamic information in deep neural networks. And that really is our goal of this paper, right? Is given a model trained for some video understanding task, we want to be able to quantify the static and dynamic information contained in that model. And so we come up with a metric and we show the efficacy of the metric on two different tasks, action recognition and video object segmentation. But for this talk, given the time constraint, I'm going to focus on action recognition. So please come visit the poster after to see the remaining results. But before I go into the approach, I want to actually define what do I mean when I say static and dynamic. So when I say static, what I'm talking about is information that's recoverable from single static frames, like photometric properties or textures or the background of a scene. When I talk about dynamic, I'm talking about information that's retrievable from correlating information across time, right? Like an object boundary and movement, or changes in lighting or motion of objects. So now that we've defined what static and dynamic information is, I'm going to go through the approach and how we quantify it. So given a pre-trained model and some video data set that we want to interpret, we're going to sample a video from that data set. Here's a video from something. Then what we're going to do is sample a factor, either static or dynamic. And if we sample static, we're going to perform what's called a static perturbation. So we're going to perturb the static information in the video. And what we do is a form of video stylization. So a recent video stylization approach, which perturbs the static information, but retains the dynamics. If we sampled the dynamic factor, we're going to perturb the video dynamically. And what that entails is the same styled video, but temporally shuffled frames. So now we have our dynamic pairs and our static pairs. We're going to feed them through our pre-trained model and output some representation Z. And what we're going to do is actually measure the mutual information between the static and dynamic pairs, okay? And so the overall metric is going to be via the softmax over the factors, the relative static versus dynamic information that the network captures between those two pairs across the data set, okay? So now we've defined our metric, we can quantify static and dynamic information in various models. We'll go into the empirical results. So first, we decided to look at action recognition architectures. And we're gonna study the most popular data set probably is still Kinetics 400 or some version of Kinetics. And we looked at single stream 3D CNNs as well as two stream 3D CNNs and recent transformer models, okay? So what we're measuring here on the y-axis is the number of dynamic channels versus static channels normalized among all of the different blocks or layers of the network, okay? So static is gonna be in red while dynamics in blue, and each model has its own marker shape. So what I want you to take away from these results here is that every single model at every single layer is biased towards static information, except for the fast branch of the slow fast model. So this points to the slow fast model actually being valid in a mechanism for extracting motion information in that fast stream. So we also looked at a number of different data sets. So we trained models on kinetics, something V2, and diving 48. So previous work has supposed that diving 48 actually has the least amount of appearance bias because all the backgrounds are basically identical, right? They're all dives, it's all pools and things like that. So we wanted to test if this was true. So what we're gonna do is we're gonna, for two different models, measure the number of dynamic units contained in the model. So here are the results. And what I want you to draw away from this is that diving 48 and kinetics are basically the same amount of dynamics encoded in the model, right? And we were a little confused. We thought diving 48 would have more dynamics, right? So in order to investigate this further, we performed another experiment where we trained the models on shuffled frames, okay? And then what we did is we calculated the relative performance drop from normal frames to shuffled frames. And so you'd expect a dynamically heavy data set would be very difficult to solve if the frames were shuffled, right? And that's what we see with something B2. But in fact, diving 48 and kinetics were quite similar. So the conclusion here is that if we want to evaluate dynamics in video understanding for action recognition models, we should do it on something B2. But looking into the future, right? And we talked about this a bit earlier today. How can we use this as an application or an intervention in our model, right? To make the algorithm better. So beyond explainability, how can we use this as an intervention? Well, we asked two main questions. The first question was, is it actually possible to manipulate the biases of our model, okay? And if it is, the second question we asked is, what is the resulting performance change, right? What is the impact on performance if we can manipulate these biases? So in order to do that, we're going to propose a new type of dropout. So here we have standard dropout, our standard, action recognition classification. You have your fully connected layer, and we randomly sample units to mask out to 0. So our static dropout that we proposed, we're going to sample the units to drop out based on the static bias of the unit. So let's go through the approach. So given a video V1, we're going to temporally shuffle the frames to generate a video V2. We pass both of the representations through the model, and now we have, remember, our static pair. So using these representations, we're going to calculate the mutual information for each channel and then perform a softmax over all the channels to get a multinomial distribution where the probability is relative to the static bias of the channel. We then drop out the units based on that distribution. And the goal here is to debias the model from static information and towards dynamics. So let's see the results. So remember our first question, can we manipulate the biases? So we have two metrics that we're going to analyze to answer that question. One is that relative performance on shuffled frames. And the second is using our metric, the fraction of dynamic to static dimensions, okay? And we try a number of different dropout ratios to see if we can actually have a dose-dependent bias manipulation in our model. And in fact, that's exactly what we see. The performance on shuffled frames decreases as the dropout rate increases, and the dynamic bias of the model increases as the dropout rate increases. So yes, we can manipulate the biases of our model. So in terms of the second question, what is the impact on performance? We target a data set called the something else compositional split. It's a split of something B2, where the objects used on the training set are completely disjoint from the objects used for the same actions on the validation set. So there's a reduced amount of object bias in the action manipulations. So again, we have two metrics. One, of course, is the top one accuracy. And the second is the dynamic bias to see if, does the bias correlate with any improvements on performance. Our baselines are no dropout as well as standard dropout. And compared to those baselines, static dropout increases the bias and also has a significant improvement in performance. So yes, we can manipulate the performance as well, and the performance is improved for some dynamically heavy tasks. So in conclusion, we first introduced a new metric for quantifying static and dynamic information in deep neural networks. We use that to interpret and explain architectures as well as data sets. And finally, we used it as an intervention and show that we could actually impact the performance in a positive manner using our metric. So thank you for listening. Come visit our poster to see the rest of the results, and you can find the paper and the project page up on the slide here. Thank you.
There are no questions on Zoom at this point. I have a question if there aren't any in-person questions.
You can ask Dipti. So far, we don't have questions from the audience.
So I wanted to understand the relative drop in the performance plot. Was that top one accuracy? Because the drops seem pretty high, like 40% and 45%.
Yeah, it was top one accuracy. So the drops, you're right, are not as significant when you consider like top K, where K is 5 or more than 1. Yeah.
Were there more drops for specific categories, like I don't know, push-ups, or like where there is a repetitive motion where shuffling of the frames can mess up the action?
Yeah, so we actually did some experiments, and while we didn't find the improvement correlated with dynamic classes, which was a bit strange, it actually correlates with the frequency of the data. So we see improvements mainly on the rarest classes in the data set. We actually did an experiment where we took the 10 most common classes and decreased it and retrained the model. And as we decrease the fraction of data, we actually keep doing better than the baseline. So we're not actually 100% sure why, but we're doing better on the least frequent classes. Yeah.
Okay, thank you.
Thank you.
Okay, I actually have also one question. So remember the slide where you were showing the diving data set? So what was the term? Not dynamic enough?
Yeah, you don't need temporal information to.
So, which reminded me of something that I remember from a long time ago, where the first video tracking competitions, when they were doing this on diving data sets, a good baseline was just to put like a bounding box in the middle of the video, and it worked amazingly because the camera person was doing the tracking. So is that why the dynamic information is gone, or is there something else to it?
Yeah, so we spent a bit of time investigating this, and what we believe is that it's actually all you need is basically a histogram of poses. So if you look at the data set, if you're gonna rotate, you need to put an arm up to create torque, right? And if you're just flipping, like in that video, you have to keep both arms down. If you glimpse whether you're taking off the diving board forward or back, you're narrowing down the classes just by glimpsing the correlations in the pose. So that's what we think it is.
I see.
Great. We have one last question, maybe from Zoom. How much is the static dynamics interpretability correlated with sampling rates?
Yeah, that's a really good question. So we did some experiments where in the slow fast model, we actually varied the sampling rate to see if the fast branch captured more or less. And there is slight changes, but not a significant amount. But I do think that's an area where we could explore more, because obviously sampling rates and action recognition is an open problem, like how much to sample and what the sampling rate is. So I think that's an interesting question.
Okay, that was a great talk. Let's thank the speaker once again. And let's welcome the next speaker. Just a second. Okay, so Vipin. Okay. Just to put it on the, okay, and this was taking a bit of the screen there, so let me just try to kind of hide it.
Yeah, the mic, is it okay if I?
Oh, yeah, you can do that.
All right. Hi, everyone. I'm Vipin Pillai. I'm a PhD student at the University of Maryland, Baltimore County, and I'm here to present our work, Consistent Explanations by Contrastive Learning. This is a joint work with Soroush, Ashley, Dennis, and Hamid. Yeah, okay.
Oh, now it should work.
Thanks. Okay, so let's consider a standard deep neural network. And we use an explanation algorithm like GradCam to arrive at the explanation for the model's prediction. So here we consider an image of image culture of belonging to the category vulture and an explanation corresponding to the image. Now, our goal is actually to improve the explainability of a given model. Now, ideally, if we wanted to do that, we could just ask a human annotator to provide supervision for corresponding to the explanations. But we face a problem, as in the annotations for explanations are not straightforward to obtain. Here we show an example of an image belonging to the car category and 3 valid explanations for the car decision. So we see a heat map highlighting the windshield regions, the windshield and the body, and also another valid explanation is maybe the entire semantic segmentation mask. So another problem with explanation annotations is that explanation is often dependent on both the model as well as the input. To mitigate the lack of explanation annotations, we borrow ideas from self-supervised learning. We use a contrastive consistency constraint on the explanation instead of the embedding space. Here we see an image belonging to RV and an augmented version of the RV image, and another image belonging to the Puma category and an augmented version of the Puma image. Now, we can use the standard algorithm like GradCam to get the explanation heat maps corresponding to these original image and the augmented version of these images. We observe that the explanations corresponding to the original image and the augmented versions of the image are not really consistent. With our method, we expect the model to exhibit explanation consistency with respect to spatial transformations. Diving deeper into our method, let's consider a query image belonging to the category vulture, and it's trained with the standard cross-entropy loss. We can use an explanation algorithm like GradCam to get the explanation heat map. And now we can perform an augmentation on both the original image as well as the explanation heat map. So we arrive at the augmented image and the augmented version of the query explanation heat map. And we can also obtain the explanation heat map corresponding to the augmented image. Now, ideally, we want the explanation heat map corresponding to the augmented image to be close to the augmented heat map. But encouraging a constraint for both of these to be similar might result in a model having a trivial solution like uniform heat map. So for example, we might get a heat map that uniformly highlights all regions of the image. To get around that, we introduce a set of random images and corresponding explanation heat maps for those random images, and we call those negative heat maps. And we use that in conjunction with the positive pair, and we use a standard contrastive loss to encourage the model to have consistent explanation. And we use this together with the cross-entropy loss to arrive at our loss. And we use the lambda hyperparameter as a trade-off between the two loss parameters. To evaluate explanation consistency, we are interested in using a metric that tries to measure consistency with respect to human priors. So the metric that we use here is called content heat map. It was introduced in our prior work that was introduced in Pillai 2021. So here we use the object annotated bounding boxes, and we measure the explanation heat map that lies strictly within this bounding box. And then the content heat map is simply the percentage of heat map that lies within this bounding box. Now we present our quantitative results on the ImageNet dataset. We present results on two networks using ResNet 18 and ResNet 15. And we report both the classification accuracy and the content heat map metric. And we show that our model obtains comparable classification accuracy, but is able to significantly improve the content heat map metric. We also report results on fine-grained datasets. We use 4 fine-grained classification datasets, and we actually observe that we are also able to improve the classification accuracy when it comes to fine-grained datasets. Now, our method, intuitively, we expect it to focus on more object discriminative regions. And this is meant to help for the task of fine-grained classification, because among the classes present for fine-grained classification, there are very minor differences between the class instances. And our method actually helps the model to also improve the classification accuracy. And we also show experiments that we are able to leverage unlabeled data, since our method does not really need labels. Now we present some qualitative results. So we have the original set of original images and the GradCam heat maps corresponding to the baseline model trained with just the cross-entropy loss, and the heat maps corresponding to the model trained with our method. And we observe that our method is able to reduce the dependency on the background contextual data. So for example, for the snowmobile object, we observe that compared to the baseline, our method is able to reduce the dependency on the rider's helmet. We also show results for some of the other fine-grained datasets. Here we show it on the Caltech birds dataset. And again, our method has reduced dependency on the background pixels and reduced contextual bias. Some more results on the Stanford CARS dataset. In the last column, we show an interesting failure case where our method focuses on the Mercedes logo present on the building, in addition to the regions on the car. We also show results for an ablation study where we compare with the CGC method that doesn't use negatives. We wanted to understand the importance of the negatives And we, as discussed, we already had an intuition that it might result in explanation heat maps that are uniform, and we actually observed that that is indeed the case. And our model is able to specifically focus on the object discriminative regions. In conclusion, we introduced a method to train models that are more explainable. And our method doesn't really need annotations for explanations. And we report results on ImageNet, Unrel, as well as 4 fine-grained classification datasets. And the fact that it focuses on the most discriminative regions of the image, it acts as a regularizer and is able to improve the classification accuracy in fine-grained settings. And we also leverage unlabeled data to improve results for 1% ImageNet subset, as well as limited label settings for fine-grained datasets. Our PyTorch code is available at this link. Thank you.
Thank you. Do we have any questions remotely?
No, I have a question, but I'll wait if there are any in person.
Is there anybody from the audience? Yeah, you can ask. You can repeat his question.
Sure. Yeah. So the question was, what kind of augmentation do we use for our method? So we use the standard random recess crop augmentation that includes horizontal flip and scale augmentation, aspect ratio augmentation. Yes. No. Yeah. Sure.
Dipti, you can go now.
Yeah. How are the random images being selected? It could be the case that the random images GradCam could also fall in the same pixel regions as the original images.
Yes, you are right. Yeah. So the intuition for the presence of the negatives is that we don't want the model to learn a trivial solution, such as a uniform heat map, or focusing on just a central region. So to pick the negatives, we just randomly pick, for example, if for a batch size of 256, we could use one as a positive pair, the rest of them as negatives, and we use the top predicted classification class category to obtain the GradCam heat map and use that as the negative. It can overlap with the positive, but our intuition is that to satisfy the constraint, the model will learn to highlight the object discriminative regions.
And in case if the images have, say, multiple objects, GradCam is known to spread out its weights when the images are super busy. Did you run into those issues, and how does your model perform on that? Yeah, that's an interesting question. You're right. So far, in cases where there could be multiple instances, we might face a situation that the augmented and the original image might highlight different regions. And we didn't run into those issues because we are using image-centric datasets like ImageNet and even fine-grained classification datasets. But yes, yeah, that's an interesting problem that might arise. Okay. Thank you.
One more question from the audience, and then we move on to the next topic.
In addition to limiting the area of the heat map, did you try to maybe make the heat map discriminated on zone? That is, train the classification discriminately by the heat maps that or would be different?
Sorry, I didn't understand the question.
Did you plan to make the heat maps discriminated to the classes in order to fight the uniform problem?
Yeah, so the question.
Can you repeat the question?
Yeah, so the question was, did we try any methods to try to make the GradCam heat maps discriminative to the object categories? So the fact that we are using GradCam, it already computes the heat map specific to a given category. So the heat map is already discriminative for a given object instance or object class.
Okay.
Yeah, sorry, maybe I understand the question. Sorry.
Okay, so let's thank the speaker again. And let's welcome the next speaker. Okay, David.
Hello, I'm David from Graz University of Technology in Austria. I'm a PhD student. And I'm presenting OccAM's laser, the first method to create attribution maps for LiDAR-based 3D object detectors, which allows you to better understand your models. This work was done in collaboration with Georg Krispel, Horst Possegger, Peter Roth, and Horst Bischof. Driven by the race to autonomous driving, there's a huge interest in 3D object detection on LiDAR data. This is reflected by the number and sheer volume of public data sets published recently, or by the competition on the corresponding detection benchmarks, like on the KITTI 3D object detection benchmark. Almost all of these models here are based on deep neural networks. And while there is an extensive research focus on improving these detectors, the explainability and the interpretability of these models is almost unexplored. Here, for instance, we see an example with two car detections. And if you look more closely, we see that the right bounding box corresponds to a true positive car detection. But for the red bounding box, the detector misclassified a dumpster as a car. And especially in a safety critical domain, we have to ask ourselves, what are the reasons for these misdetections? And what are the characteristic features of a car in the eye of a detector? If you look at 2D image models, we already saw today, saliency maps or attribution maps are quite well established. They show us the most important regions in the image for the classification. And basically, these methods can be split in white box and black box analysis. In white box analysis, we have access to the input output, and then the model architecture is known, and we have access to the gradients and parameters. Whereas in black box analysis, we just have access to the input and output. In white box analysis, usually the gradient of the output with respect to the input image is used in addition with the activation of the intermediate layers. Whereas in black box analysis, these methods attempt to analyze the model's behavior by changing the input and observing the effects on the output. Compared to 2D models, there are only a few approaches dealing with attribution maps for 3D point cloud models. And these exclusively deal with point cloud classification models trained or operating on synthetic data like a ModelNet dataset. In addition, these methods are white box methods requiring a special model architecture. And therefore, these methods are not applicable to 3D object detectors, where we have to localize and classify the objects, which usually goes hand in hand. And in addition, these architectures usually consists of complex architectures, including non-differentiable steps, which do not allow gradient-based approaches. So now I want to present you our approach. Given a point cloud X, a corresponding detector F, and detector F and the corresponding detections F of X, our goal is to create an attribution map for each detection, which shows us the importance of each 3D point on the detection. OccAM is based on the observation that an object will be detected less accurately or not at all if important input areas are removed. And we take advantage of this by testing the model with tailored sub-point clouds and analyzing the impacts on the detections. The first step is to downsample the input point cloud and to create these probing samples. And we propose a voxelization-based strategy, which allows fast detector probing while still obtaining information at point level by randomly shifting the voxel grid for each sampling for each sample. The points within a voxel are then kept with sampling probability PV. Choosing this sampling probability is a crucial step. If we remove two less points, then the objects will always be detected accurately and we do not gain any information. Similarly, if we remove too many points, then the object will never be detected, we also gain no information. Now for LiDAR data, the density or the number of nearby points, the voxel density, drops significantly with the distance to the LiDAR sensor. In fact, we can approximate this using a second order polynomial. and use its scale inverse to compute the sampling probability for each voxel depending on the distance. And using this approach, we can challenge the detector appropriately, regardless of the distance to the LiDAR sensor. These subsampled point clouds are then passed through the detector to obtain the corresponding detections, which are then compared to the original detections using a similarity metric we proposed. And this similarity metric addresses the changes in confidence score, scale, translation, and rotation. And the final attribution map is then computed as the weighted sum over all input samples, weighted by the similarity metric for each detection. And now I want to show you some results. Here are results from for a point pillars model trained on the Kitty dataset. And what we found is that for car detections, for cars, the license plate is a very distinctive feature because of the high reflectivity of the license plate. But but also the roof railings or the A pillars and B pillars are very important. And we argue that these fine structures in combination with the transparent windows are very distinctive for cars. And these features are especially important if the license plate is occluded, like on the left side. For pedestrians, we found that the head-shoulder silhouette is consistently the most important region for detecting pedestrians. Also note in the left example how well OccAM can analyze individual detections even in a crowded scene. For cyclists, we also found that the head-shoulder silhouette was very important in addition to the reflectors on the front and the back of the bike. OccAM's laser can also be used to analyze false detections. And now we see the example from the beginning, the dumpster. And the attribution maps reveal that thin structures at the top were responsible for this detection. Most likely, the detector interpreted this as a roof railing of a car. And on the right example, the detector was misled by the license plate on this trailer. We also evaluated OccAM quantitatively in a point dropping evaluation. And if we remove the points within the bounding box according to our attribution maps, the mean confidence score and the mean IOU drops significantly faster than a random selection. Yeah, but note also the random selections remove points directly belonging to the object. An interesting finding was that even if we remove all points within the detections, the mean confidence score and IOU doesn't go down to 0. And the reason is that distinctive cutouts on the floor were responsible for these detections, and the attribution maps show that yeah, these regions are more important for this detection. We also averaged our attribution maps to get the characteristic, to analyze the characteristic features of a class. And we found similar results to the individual examples. The license plate for cars, as well as the A and B pillar, are very important. And for pedestrians, the head-shoulder silhouette is very important. Okay, thank you for your attention. And if you want to try it on your own detector, please check our online resources where we also show additional results, or find us at the post session tomorrow morning.
Thank you. Any questions from the audience? Dipti, are there questions on your side from Zoom attendees?
None from the attendees. I was just curious, how sensitive is this analysis or are these results to the dataset? Is this Kitty specific, or have you looked at other 3D datasets?
Yep. We also did it for the Waymo dataset. You have to adjust then, of course, this sampling probability function, but it works also for the Waymo dataset.
Got it. Thanks.
Okay, let's thank the speaker once again. And we have our last spotlight for the workshop, Moritz. Share it. Okay. So,
all right. Does it work?
Yeah.
Okay. All right. Hi, everyone. So my name is Moritz Böhler. I'm a PhD student at the Max Planck Institute for Informatics. And I'm really happy to be able to discuss with you today my work on B-cos networks, which is a novel family of deep neural network models that is designed to inherently produce highly detailed explanations for their decisions, as you can see, for example, here in the bottom. But before I go into the details of how we obtain these explanations, let me take a step back and kind of set the stage a bit. So we work in the field of image classification, where, for example, for a conventional DNN-trained ImageNet, you can feed this image of two birds to the classifier, which might then predict that this is a goldfinch. But specifically in ambiguous cases like this one here, you might want an explanation for your decision, right? Because you would at least want to make sure that the model predicts or makes its predictions based on the right reasons. Unfortunately, to this day, it's still difficult, and there's no reliable method for extracting model faithful explanations for deep neural networks in general. And this thus remains an open research question. But instead of designing a post hoc explanation method, as is very commonly done in this work, we try to directly optimize the network, both in terms of architecture as well as during training, to produce explanations for their decisions. And concretely, the way that we do this is, on the one hand, by defining our models in a way that they are dynamic linear, which means that they linearly transform their input X by an input-dependent matrix W of X, as shown here. And this approach is thus designed to specifically take advantage of the simplicity of the linear transformation on the one hand, whilst maintaining high modeling capacity by allowing us to adapt the linear transformation matrix according to the input. And we do indeed find that if you do this carefully and constrain this linear transformation matrix appropriately, that we get very detailed explanation for the model decisions as shown here. In particular, the explanations that we obtain are actually a direct reflection of the linear transformation matrix that the model learns during training. Or to be more exact, as shown here, it's the row corresponding to the class that you try to explain that we visualize. And these explanations, as you can see, are highly detailed, focusing on very specific class discriminative features, as for example, the eyes of the owl here in the image to the left, or the eyes of the feathers of the peacock to the right. And not only do the explanations give a lot of detail, but importantly, they are actually an accurate summary of the model computations. Because if you look at the equation to the left, the model computes its output via this linear transformation that we visualize, and you can also therefore retrieve the model prediction by simply computing the scalar product between the input and the explanation. And given that we explicitly optimize our networks to be explainable under this linear transformation matrix, we also find that these inherent explanations compare very favorably to post hoc explanations evaluated on these models. But how exactly do we do this? So on the one hand, I said we define our models to be dynamic linear. And to understand how we do this, let's zoom in on the network, which is defined as a sequence of actually dynamic linear transformations. So we don't produce this linear transformation in one step, but instead each layer in the network computes a dynamic linear transformation of its input. And given that there are no additional nonlinearities in between, we can summarize this consecutive application of linear transformations by just one single linear transformation that accurately summarizes the entire model. And to be more concrete, the way that we do this is via our novel B-cos transform, which is a slight modification of the linear transformation that is abundantly used in deep neural networks. So I highlight here in blue the differences to the linear transformation. And specifically, what we do in these B-cos transforms, as you can see, we add this additional parameter B, which encourages alignment between weights and inputs during training, specifically in a way that, as you can see, or as I try to visualize here, for non-aligned weights and inputs, the model has no way of producing large outputs anymore. And the only way to achieve large outputs is by actually learning to align the weights with the inputs. Exactly. So, and coming to the results, so one of the key features of our models is, or of our approach, is that it is not, we don't have to start from scratch, but we can actually integrate our B-cos transformation into standard networks, as it's just a slight modification of the linear transformation. So in order to convert standard models such as ResNets, SenseNets, VGGs, or Inception nets to B-cos versions of these models, we only need to effectively change the linear transformation of these models, and we see that we can obtain very similar classification accuracies. Similarly, apart from just getting nice qualitative results in terms of explanations, we also find that on quantitative metrics for explainability, the model inherent explanations consistently across all the tested networks fare better than post-hoc explanations evaluated for these models. And maybe one last thing before I come to a close. As I said, each of the layers of the network is actually defined as a dynamic linear transformation, which also means that every neuron or every activation in the network is actually computed as a dynamic linear transformation of the input and can be explained in the same way as the network output overall. This means that we can also start explaining individual neurons in the network as shown here. Specifically for this specific neuron here, neuron 790, we show the highest activations in these images that were sorted according to how highly the neurons activate. And we find that the highest activations of the neurons are focusing consistently on cars in the image. And we find this is not only like this specific neuron that does something specific like this, we also find face detectors, tongue detectors of dogs, for example, or which is important for debugging deep neural networks, we also find that some of these neurons specifically trigger for watermarks in the images. So to summarize, we introduce an inherently interpretable approach for building, introduce an approach for designing inherently interpretable B-cos networks, which is an approach that is compatible with standard DNN architectures and results in models that achieve competitive performance on the one hand, whilst providing highly detailed explanations at the same time for their decisions. And with this, thank you very much, and I'm happy to take questions.
Yeah, you can use the microphone. So just make sure to repeat the question.
Yes.
So this is down from our university. So I have two questions. So the first one is for the network that do not explicitly use the linear transformation like the VIP. So how can we incorporate that? And the second question is how can you magnify the trade-off between the accuracy and the interpretability?
Okay, so I'm trying to repeat because I like the audio doesn't get here as well. But so the first question was, how does this work, for example, for models like vision transformers?
Yeah,
Yes. So okay. So in terms of trade-off between interpretability and accuracy, maybe I just quickly go back to the slide. So we find actually that while we do see some trade-off in terms of accuracy, so we do lose some accuracy, we can actually almost maintain the same classification accuracy when converting standard models, and just additionally obtain much more interpretable explanations for the decisions. And regarding other network types, such as vision transformers, this is actually something that we are working on, and we'll be releasing a preprint on how to also integrate this into vision transformers in a short time. Thank you.
Thank you. Are there any?
Mm-hmm.
Okay.
So the first question is, what is the ground truth for the because of branch? Is it supervised?
Yeah, that's a good question. Maybe that didn't become entirely clear. So this is completely unsupervised in terms of the explanations that the network obtains. The only thing that we optimize for is for classification accuracy. But the way that we constrain the networks makes sure that the only way that the network can actually achieve a low loss is by aligning the weights with the inputs. So what we show here is not really something, we don't optimize against the ground truth, but instead we optimize the networks to produce such easily interpretable classifications. And this is just a reflection of what the model computes without being necessarily a ground truth explanation in that sense.
Okay, and the last question, how is your method different from self-attention models?
Well, self-attention models, so what we design here is a type of network that overall computes the output as a linear transformation of the input. And self-attention models also have, in part, they have this aspect that the self-attention layer also computes a linear transformation of the input to that layer. But typically, self-attention models are combined with other nonlinear modules additionally. So you cannot explain a self-attention model necessarily from front to back as well as we can do for these networks, if that answers the question.
Okay, let's thank the speaker again. This was a great talk. Okay, so I'm gonna stop sharing because the next up is Bin.
Yes.
And
yeah, it's a great pleasure that we invite Bin Kim. She's a staff research scientist at Google Brain. She's done tons of work on building interpretable methods and models, both post hoc and also inherently interpretable models. We are very, very excited to have her here and give the talk. So take it away, Bin.